Hello everyone, hope all of you are doing well. So just briefly recall that we have discussed fundamental theorem for line integrals, and then we saw several consequences, we saw several definitions. So for example, the meaning of integral vanishing over a simple closed curve, and that conservative and so on. So we had several observations, and we had this type of domains which we called simply connected domains, basically the domains which do not have holes, isn't it? So these definitions will be used, and today we are going to talk about this very important theorem which we had been trying to prepare for so far. So this theorem is called Green's theorem, and this is precisely the counterpart of fundamental theorem for double integral. Okay, so basically we are going to have a double integral. Okay, so there are going to be regions in R2 over which we want to integrate, and then you expect that fundamental theorem would have this integral relates to an integral which is over a one dimensional thing, okay, or the curve which is the boundary of that domain. Okay, so this is precisely we are going to discuss today. So as I said, this is a counterpart, okay, and there are going to be more than one statements for this, so we will slowly go about it. So what we are going to do is we are going to also need some definitions in the process. Okay, so you see that you consider a domain, and then the boundary generally is denoted by a del D, but often we will not write it because we are writing the boundary or the curves as C. Okay, so that is what notation we will use. So we will consider a domain, okay, nice domains of course, and then the boundary curve we will write it as or denote it as C. Okay, so that simple closed curve. Okay, so these are the curves which meet at the end point and do not cross in the in the interior. All right, so we say that a simple closed curve, so you imagine a simple closed curve which is okay here also, then we say that this curve is positively oriented if you trace it out in a counterclockwise direction. Okay, so what does it mean? So basically you are moving this way, you see this is the boundary, and then you are moving along this in a counterclockwise direction. Okay, so imagine a circle first and then give the counterclockwise direction, but the domains need not look like discs, and hence the curves need not look like a circle. Okay, they can be any simple closed curve. So this is what we are going to assume. So this is called the positive orientation of the simple closed curve. Okay, another way is like when you are moving along this, sometimes this definition is also given. So when you are moving along the curve, the region which the curve encloses, so what is the meaning of the region? See, this is a curve, then there is something it bounds, so that is the region I am talking about. Okay, so you look at the interior part of this curve, then so if you are moving in such a way that no matter at which point you are, the region always falls on the left hand side. Okay, so that is precisely the positive orientation. Okay, so this is something which you keep in mind, that because there is a sense of direction for integral, so we will always consider positive orientation, and if you have a negative oriented curve, then you put a minus, reverse the direction, and you consider the corresponding integral. All right, so keep in mind that for simple closed curve, the positive orientation means the counterclockwise direction. All right, so Green's theorem, okay, it basically consists of these things. You consider positively oriented, and then you allow piecewise smooth simple closed curve in R2. Okay, so this is precisely the definition which involved the positive oriented simple closed curves. So you also allow that piecewise smooth. Okay, so if you have a domain like this or curve like this, and look at the domain which is enclosed by this curve. Okay, so imagine this situation, that this is your curve and then this is your domain. Okay, so this is what I'm saying, and you consider a vector field for which the functions p and q, they have continuous partial or derivatives of first order. Okay, and here we are saying that this is happening on an open region that contains this. Okay, so this is just to avoid any kind of singularity or any kind of problem in order to compute the derivatives for p and q. So you say that the functions p and q they have continuous first order partial derivative on an open region containing this D. Then you have this relation of this double integral, which is a double integral of these derivatives, and this is basically the line integral of P and NQ. Okay, so this is precisely you expect that the fundamental theorem, it relates integral on something to the boundary. Okay, so this is precisely we are doing here, we are able to do that. Okay, and this is I mean you have to say that this positively oriented thing is part of the definition. Okay, so we will see several applications and several examples of this theorem. This is really a powerful theorem, and also there are more than one ways to describe this result which we have right now. Okay, so we will talk about those also, and here we can also relax certain conditions which we have put forward here on the domain and the curve, so that also we will talk about. All right, I will give you a brief sketch. In general, this theorem is not so easy to prove. Okay, it requires a lot of things, but for the domains which we have been talking about, okay, like the ones which I have written over here, this is the domain. If you remember that when we considered the double integral, these were the general domains which we handled. Okay, so we consider a domain which we have been talking about, and in the context of this domain we are going to give you a proof. Okay, I mean, to make it even simpler, what you can do is actually you can consider a rectangle. Okay, so instead of g1x you take c, and then g2x you take d. So that that also you can try and write down, but of course that's going to be immediate from this proof. Okay, so if you want to prove this, it's enough to prove. You look at the term corresponding to p here, so that is the line integral of p with respect to this x, and then there is a term with respect to p over here. So what we are going to do is we are going to rather prove these two equations, that this line integral of p is same as this with minus sign in this double integral, and then similarly this quantity is same as the double integral of del q by del x. Okay, because this is sum of two things, integral is linear, so you get the result, isn't it? And the proof of these two guys, these two equations, is more or less same. Okay, the idea is same. So I give you the proof of this or this. Let me see which one I have written, and then the other proof you can just write it down. Okay, all right. So basically what we will do is we will evaluate this double integral and we will evaluate this line integral, and so that whatever we get, they are the same quantities. All right. Okay, so we know that because our domain allows us to use Fubini's theorem, so I can immediately write down this double integral using the Fubini theorem in this fashion. Okay, now if you just look at this piece, oops, this goes. Okay, just look at this piece, then this is a situation of just a single variable, because the variable by is being integrated out for each fixed x. Okay, so here I can apply the fundamental theorem of calculus, isn't it? And if you do that, this is what you are going to get, and then what is left is this integral of this quantity. Now we do not know what is this p, so if we stop here, because we do not have any concrete expression for p. So what we get is this quantity. Okay, now we try to compute the line integral, and we say that we are exactly going to get this. Okay, now so you have to go back, because line integral will involve the whole boundary. So this domain, first of all, you need to write down. Okay, draw the picture. So the domain is x variable is moving between a and b, and then y variable is moving between these two curves. So you draw this region. Okay, the shape is not important. I mean, this curve can be different looking, but it's going to be of this type. All right. Okay, so the boundary curve is made of these four curves. Okay, so this is each piece is smooth and they are joined together, so this is a piecewise smooth curve. Okay, and we are considering positive orientation, so the orientation is going to be this way, this way, this way, and then this way. Okay, this is the counterclockwise. And now we know that in order to compute the line integral over the C, we have to compute the line integral over each curve, then we are done. Okay, now particularly these two curves over here, if you stare at it, because we are going to integrate over these curves with respect to x. Now this curve and this curve is x is fixed here, x equal to a, and similarly this curve x equal to b is fixed. So there is no change in x. So that means that dx, if there is no change, dx is going to be 0. So integral of p with respect to x along these two curves, okay, this way and then this way, they are just going to be 0. Okay, so this part you can discard when you are computing the integral over this simple closed curve or piecewise smooth simple closed curve, which is the union of these four things. Okay, so what is left for you? Consider this integral and consider this integral. Okay, but you have to be a little bit careful. This curve has a positive orientation, but this curve, because we are just talking about alone this curve, now this is going from b to a. Okay, so this is a negative curve, negatively oriented curve. Okay, so you have to be a little bit careful. Okay, so let me do it. Integral over along this c1. So you write the parameterization. So parameterization of this curve is given by this function g, and the variable is changing from a to b. Okay, so this is precisely you have. Okay, and that's all, because we cannot solve it further because there is no explicit expression for p and g. So we just leave it like this, and this integral along c3 is going to be, as I said, because this is going in the opposite direction, it's not starting at a. Okay, it's rather starting at b, so there's going to be a minus sign. Okay, now you have to just put all these things together. There's no contribution from here, and these two guys only contribute, and you see that you get these terms with proper signs which you wanted, and this is precisely this equation. Okay, so proving this theorem for the simple domains is fairly easy. However, if you want to do something general, that's not easy to prove. All right. Okay, so this is a situation where we can relate a double integral, okay, over a nice domain enclosed by a simple closed curve with positive orientation with a line integral. Okay, now we can have situations which are slightly more general. Okay, and then we want to talk about the Green's theorem. So imagine this picture. Here what you have a domain D1 and then you have another domain D2. Okay, and along this curve, okay, which is a line over here, they have been pasted. Okay, so technically what you start with two domains and then you paste them along a common boundary. Okay, so this is, this line is just it was there in the book, but you can take a curve also here. The boundary of D2 and D1, they can meet on a curve also. Okay, that's not a problem. So can we have, so basically now you see that D1 and D2 separately, we have the Fubini's theorem, the Green's theorem. Okay, now I have pasted. So what is going to happen if I look at the union of D1 and D2? So the boundary is going to be the outer part. The line will be missing because that's not the boundary now anymore for the union. Okay, so we have the Green's theorem for D1, we have Green's theorem for D2. Do we have Green's theorem for the union? Okay, this is what so yes, you can do that, and all you have to do is basically just realize the following thing, that okay, so here I have written that we can extend Green's theorem to domains which are union of finitely many domains, okay, as shown in the figure. Okay, if you put them separate, then there is no point of talking about Green's theorem over the union, correct? So they have to give you a nice domain, because if they are sitting without any if they are disjoint without any common boundary, then there is absolutely no point. Okay, so we look at this kind of situation, and then you can keep one more over here and then attach one more over here, all that you can keep on doing. So then we have the Green's theorem for the union. Okay, and how does one prove it? It's fairly easy. Okay, what you have to do is, so look at this. So this is your D1. So the boundaries, let's say, start here, it starts all the way here. So this is your curve C1, and then you go this. Okay, so C3 is also part of the, so here you have to put this kind of direction, correct, because you want counterclockwise. So C3 is moving in this way. So C3 and C1, they give you the boundary for D1. So this is one boundary curve. Okay, that means I have Green's theorem for D1 and then C1 union C3. Okay, now for the other one, the positive orientation on this side is this, and then when you reach here you have to go this way, that means you have to basically go follow the minus of C3. Okay, so the boundary for D2 is going to be C2 as here and minus C3 over here. Okay, so now what we need to do is, you look at the double integral over D, which is the union. Okay, and just separate it into two pieces over D1 and D2 and apply the Green's theorem separately for D1 as well as for D2. And what will happen, that Green's theorem basically will tell you that the integral over D1 is integral over the line integral over C1 and then C3. Okay, and C3 here is with positive orientation. When you do it for D2, it will again tell you that this integral over D2 is same as line integral over C2, but then there is going to be a term with minus C3. So when you put them together, the C3 with positive orientation here and C3 with negative orientation here, they will cancel each other. Okay, so this extra line which you have here will just disappear, and what you will get, the line integral is C1 and then C2. So you get the result. Okay, so I did not write the detail, rather you can just complete them. Okay, so this is a situation where we put two things together along a common boundary. Okay, all right. Now a third type of domains can be the domains which have got holes, so the domains which are not simply connected. Okay, so okay, this is the domain you are interested in, and what is the boundary here? Now you see there is going to be an outer boundary and you want to give a positive orientation, so the orientation will be like this, so that your domain always lies on the left, whereas if you go to the inner part, so there is inner boundary also here, correct. Here the boundary will look like opposite because you want positive orientation. So the boundary of D consists of two curves, the C1 and then C2. Okay, so C1 is having this positive orientation, and C2 you have to give the orientation like this because you want the domain to fall on the left always. Okay, so when I talk about the boundary curve being positively oriented for this kind of domain, then you have to be careful that the outer part is going to go this way and the inner part is going to go the opposite way, because because the definition of positively oriented curve means this: the domain always falls on the left when you move with respect to the positive orientation. Okay, so this you have to be a little bit careful. Okay, so the basically idea is, we can have vector fields which are having some problems, like the partial derivatives are not continuous or at some point. So what we do is we try to remove that part and then we get a hole. Okay, and then we want to see whether we have a similar conclusion of which we could have for the simply connected domains. Okay, and the answer is yes. So you consider a domain. I will consider a domain which is one hole, but you can put multiple holes. Okay, the same idea goes through. So this is precisely the situation we have. Then the boundary curve, as I said, it is made of two things: the outer circle and the inner circle. Okay, I should not say circle. This should be called as curves. Okay, this hole may not look like a disc or a circular one. Okay, so outer curve and inner curve, you give them positive orientation. Okay, so you see that this C2 is oriented clockwise because this comes as the boundary of, this is part of the boundary of D with positive orientation. Okay, so that is the reason. All right. So the Green's theorem, the analog of Green's theorem holds here. So this is precisely the conclusion you expect for the Green's theorem. So basically the point is that we can have, or we have the Green's theorem applicable to domains with holes. Okay, so this is precisely what you do. You consider the double integral of these derivatives and you have this line integral of P and Q. Okay, so And what one can do is we can actually prove this using the previous statements, and the proof is not difficult once you have proved the main theorem. So what you do is you decompose your domain into this. Okay, so these lines which I have put here, they are basically giving us the decomposition. So this side is d double prime and this side is d prime. Okay, so the d is being written as union of d1, sorry not d1, d prime and d double prime. Okay, and we are going to apply Green's theorem to each piece, because now this piece, if you look at this piece, I should go this way because you want positive orientation. So this is the positive orientation of the boundary curve for d prime. Okay, now there is no hole in d prime. Similarly, there is no hole in d double prime. So I can apply Green's theorem as we had in the previous slides. Okay, and you know, all I have to do is you put them together. All one has to realize here then that when we apply Green's theorem to d prime and d double prime separately, once you are going to get the boundary, I mean this line with this direction, and you will go this way and then you will come back this way, and then from here you basically, this is your positive orientation. Okay, but when I do it for d double prime, so this is the positive orientation. So when you reach here, this line is going to have this orientation, and then you come along this and then move like this, and then you are going to have this orientation. Okay, and then you come back via this. So that is the positive orientation for d prime. So you see there's going to be a line integral for d prime with this direction and with d double prime with this direction. So these integrals over this line segment will cancel each other, and similarly over here. So the idea is, like, you know, the connections which you made here, these are the connections, isn't it? Like you connected these two guys, and they just cancel each other when you put them together. Okay, so this is a very beautiful idea, that you can avoid these holes. Okay, I mean, imagine now if you have one more hole here, you know, you can do the same thing. Okay, so this is a very beautiful theorem, and we see that this hole, so and this is basically a way to avoid a possible singularity which can have, you know, at a point. So you remove a small neighborhood of that and get rid of it. Okay, so that is the kind of situation we will have, and we will have some examples. Okay, so let us talk about some examples. So this is, I mean, you can think of it as an example or a theorem. So Green's theorem can be used to compute the areas of, you know, domains in R2. Okay, so for example, if I take this nice situation that D is a disk of radius R. Okay, this is precisely because, you know, the Green's theorem on one hand, on this side, it has got a double integral. So if I put this to be a constant thing, okay, this function, if this is constant, then what you have is the area of D. So this has to give us the area of D, and this area can be computed. So the Green's theorem basically tell you that the area of certain domains can be computed using the line integral. You know, you don't have to do this is bad. You don't have to really do double integral. Okay, so you can just compute the area by using single integral, the line integral. Okay, so this is very beautiful application. Let me illustrate it. So as I said, what you want here, you want constant 1 here, isn't it? So that when I integrate, I just get there is no function here, so there is no scaling or there is no change of shape. So you are going to get the area. So in order to get 1 here, what I need to make sure that this function which I choose, okay, is equal to 1. You see here there is no information about vector field or anything. It's just the domain is given and you want to compute the area. Okay, there are several ways. You double integrate it, you draw this and then use the double integration, use polar coordinates, whatever you know that you can do. But the point is, like, you know, one question can be tackled in different ways. Okay, and sometimes you get more general answers to situations which you are not able to tackle using the old theory. Okay, so what you want here, you want to choose a vector field so that the derivatives of P and Q, this quantity gives you 1. Okay, so now when I say this quantity is 1, you need to make sure that P and Q are chosen in such a way that this happens. Okay, and they have to satisfy all those properties, that P and Q, they have continuous first order partial derivatives on the domain and so on, correct? All right, so one possibility I give you here, that you can take Q is just X, because you want 1 here, and this guy you can put 0. So there's absolutely nothing with respect to the Y here, and then when you differentiate partially with respect to X, you get just 1. Okay, so this is one possible solution. You could take other solution. For example, you could have put this to be 0 and this to be minus by. So when you take the derivative with respect to by, you get minus 1, and then minus is there, so plus 1. Okay, so there can be many or more than one solutions, and in fact there are. So what you can do is you can write down the area of this disk by in terms of this. Okay, here C is what? C is the boundary curve. So this is going to be the circle of radius r. Okay, which is precisely the parameterization, and you can very easily integrate this, because this is a line integral, isn't it? So sometimes these theorems, not sometimes, in fact that is the goal, that the theory helps to simplify the situations, and allow more general domains and more general questions to be answered. All right. Okay, now we consider one more example. Okay, so consider this vector field, and what we are asking you, that evaluate the line integral. Okay, this line integral where C is a positively oriented simple closed curve enclosing the origin. Okay, now here you see the C is given, there is no concrete definition of C. It's not given in terms of a parameterization. It's just arbitrary simple closed curve enclosing the origin. Okay, and of course with the positive orientation. Okay, so I mean, immediately if you think about it, we know how to compute the line integral. I know the given vector field is there, but there is a problem, because I do not know how to write down the parameterization of the curve. Okay, and also you see, if we just prove the Green's theorem, generally this question is asked in the exam. Okay, but I am discussing it because this has a very beautiful idea behind it, and it's important to go through such things, because if such a question comes in the exam, it will be difficult if you have not practiced enough. Okay, so there are 2 points here which one should notice, that look at this P and then the Q. If I look at the origin, these guys are not nice functions over there, correct, because of this x square plus y square. At the origin, this is denominator is of the order of x square plus y square, whereas the numerator is only y. So there is going to be a problem. The denominator is going to blow up. Similarly over here. Okay, so there is a problem at the origin for the P and Q. Okay, and so this problem why I am telling you, because if I try to apply the Green's theorem, what I will do, I will consider the domain which is enclosed by this curve. So that is going to have the origin inside, because this is saying that enclosing the origin. Okay, so I cannot immediately apply Green's theorem. Okay, but what we can do is, as we saw, that we can create a hole around it, so that the origin is removed, and once origin is removed, this vector field, the function, the P and Q, they are very nice, because the only problem is the origin. So but we know that Green's theorem can be applied to domains with holes. Okay, so this line integral what I have got here, okay, there is a possibility then I can relate it to a double integral, but you see there is going to be one more, because this is the outer circle in that case, or outer boundary. So when I create a hole, there is going to be another boundary. Okay, so basically the sum of these two guys is going to be a double integral. Okay, so that is what we are going to do. So we are going to consider this. So let us say this is the given the curve. This is a positively oriented curve enclosing the origin, and what I do is I create a hole here. Okay, now this hole I can create because this is a smooth curve, so it is encloses the origin. So there is going to be a small disk which I can take out without touching the boundary. So I do this. So this radius of disk can be very, very small, and call this circle as a c prime. Okay, now we consider this situation, then the integral of the boundary of this D, okay, this is your domain D. Now the positive orientation on the boundary going to mean C, which is counterclockwise here, but the C prime is not this. Okay, we have to consider the boundary with positive orientation, so this is going to be C union minus of C prime. Okay, so that is going to be the boundary of D with positive orientation. Okay, here C prime is written with positive orientation when it is considered on alone. Okay, but not as the boundary of D. Okay, this you have to be careful, like in the previous. So here I am writing it kind of deliberately, that so that you understand that when I say that the boundary of D as boundary of the curve is C union minus C prime with positive orientation. Okay, so now to this domain I can apply the Green's theorem. So that is precisely going to give me an integral or line integral over C union minus C prime, and the double integral is going to be this. Okay, now P and Q are nice, their partial derivatives are continuous, all you need to do is compute them. So compute the partial derivative of Q with respect to x, and you see that this is going to be this number, okay, or this function. Please verify these calculations, I always make a lot of mistakes. Okay, and similarly you compute this. So what you notice here, that these two guys actually are coming out to be the same, this and this. So this side what you are going to get is 0. Okay, so there is no double integral, this side you have just 0. Now if you have 0, that means that this line integral, which is basically two line integrals, one is over C and one is over minus C prime, and minus C prime, basically when I convert it to C prime, there is going to be a minus sign. So you take it to the right, you are going to get this, isn't it? So the line integral over a very arbitrary curve C has now been converted to a line integral over a circular curve. Okay, so this, now you can write down the parameterization. So as a problem which was not concrete enough has been converted into a problem over a very nice curve, okay, whose parameterization you can write down and then compute the line integral. Okay, so you compute the line integral and get the answer. Okay, and also you will notice, because the C prime comes with because there is going to be a radius, correct? So what you need to think of, that how is this integral depending on C prime? Okay, because the C prime a priori, if you just follow the proof, the same proof will work if I had taken a smaller curve here, correct? A smaller circle inside, then also the same proof would have worked. Okay, so this kind of indicates that the line integral over this C prime is not going to depend on the radius of this curve, because this side is fixed. Okay, this side is the original thing. So even if I am taking a bigger circle, the answer should come out to be the same. Okay, so that is another conclusion you should make here, that if such a situation is given and I ask you to find the integral of this, let's say of along the circle of radius 100, okay, and ask you the integral of this along the circle of radius 1 by 100, is the answer going to depend on 100? That is something you should conclude after this. Okay, so I am going to stop here, and then next class we will talk about further in this direction, and we will have some different version of Green's theorem. Okay, so that we will discuss in the next class. All right.